can you keep an eye on the timings of the presentation?
Yeah.
Okay. So.
Okay, so that worked there. Did that get replayed to the? No. So the matrix and Jabber are linked well, but the Zulip.
Zulip is not?
Is not. It works, but it's not connected to the bot. I'm typing this, isn't it?
No, indeed. But I get in Zulip the messages from Jabber.
No, those are not those.
So these were sent on the Lake stream.
Okay, yes, so it's working one way.
Yeah.
Yeah. I'll keep an eye on them all. Okay, we're at time.
Okay, so should we wait or?
Hard to know. Give it a minute.
Yeah. How many people are 35 in Miteco? So we should just remind them to sign into Miteco.
Yep.
Yeah.
So just for remote people, we'll give it another minute as people put down their cookies and coffees and come into the room. And then we'll start. All right, should we start?
Yeah.
All right, good afternoon for the people here. Good morning, good evening, whatever it is for remote people. Welcome to the Lake session at IETF113. We have a fairly full agenda today, so we'll be trying to keep the time. I think I'm going to do some of the administrivia stuff. Alicia's going to look after the technical content, but I'll be hassling people if they're using too much time or getting close to their time. So this is the note well. You should all be aware of that. You should all be nice to each other. Our agenda and links are there. I'm keeping an eye on the Jabber. We have note takers. Thank you. And as far as I can see, the Jabber room is connected to Meetecho and to the matrix stuff that's no longer supported. And it seems to be unidirectional talking to Zulip if you're using Zulip. So if you write a message in Zulip, I might see it here, but other people might not. Okay, so since this is a hybrid meeting, it's a little bit different. And since it's Monday, we may as well repeat this. So the blue sheets are for the people in the room. You need to sign in to the data tracker. So please do that to make sure you're counted. There is a on-site tool that allows you to join the mic line and to take part in polls. That's a pretty limited interface, so you might want to just join that on your phone and be in the other one on your laptop if you're doing that. For remote people, again, usual things, make sure audio and video are off unless you're presenting. I think the plan is that Alicia is going to share the slides but hand over control to the remote presenters because I think most people are remote. And again, for the chat, if you want us to repeat something, then just preface it with Mike. Okay, so our agenda, we've got 2 hours. We're on the first point. Militia will give a quick update. We have reports on hackathon, some developer feedback. Militia has some implementation feedback as well, security update. Then we'll be talking about the various pieces of analysis work that have been happening on the current draft. Joran will talk again then about some of the issues and change requests and so on that have been applied to the editor's copy of the draft, and next steps. So, does anybody want to bash the agenda? There's the first part. There's the second part. I'm not seeing anybody joining the queue or in the room. Oh, by the way, if in theory, if you're in the room here and you want to join the mic line, you should hit the button and then join the mic line, just to keep you in the right order. We'll see how that, it's a nice thing to do, but we'll see if it's needed. Okay, so I think that's the administrivia done. You can pick your next set of slides.
Okay, so hello everyone. So this is Militia speaking on behalf of me and Steven. So just to give a quick update on the status of the working group since the last IETF meeting. So we have adopted the lake traces draft just after the last meeting. We have declared the ad hoc specification in its 12th version as ready for formal analysis, and went ahead and published an article in IEEE Computer Magazine inviting the academic community to study the protocol. So the article kind of summarizes the protocol and invites the community to study it in its different models, and which proved to be a good idea because we already received quite some feedback, as you will see during this meeting. Because of that, the ad hoc specification was frozen, meaning that we did not publish any new versions in the data tracker since IETF112, but the author team was not lazy, and then they kept working on the specification in GitHub. So currently the latest version is the editor's version in GitHub. That said, we will be discussing the next steps, how to proceed and how to get organized, considering these concurrent activities that are taking place. So we will present, today's meeting is a little bit peculiar in that we have the chartered items at the end of the meeting, the items of the charter of the working group. This is because we are giving priority now to the analysis that is taking place, and the main chunk of the meeting will be given to the security analysis from different teams that are involved. So just to give a brief overview about this article that was published in IEEE Computer Magazine, it summarized, as I said, it summarized the protocol. I presented it briefly before it was even published during the last IETF meeting. It invites the community to study the protocol in the 2 models, Symbolic and the Computational, as well as to provide some feedback and code on the implementation security. So we have Eric in the queue. Eric? Oh, okay. Just as.
Oh, if you sign into the tracker for the session, you're in the blue sheet. Yeah. So the blue sheet is implicit when you sign in for the session.
Yeah, and the last point on this one is, like, if you didn't notice, once I was correcting the proof of the article in IEEE Computer Magazine, I found out that COSE stands for Common Open Software Environment Protocol. So that was kind of funny. So yes, we went ahead and corrected, but it was a bit, it was a funny situation with all the details that we've been working on in terms of this article, and then the big title coming out wrong. So yes, that was corrected. So, as I said, today's meeting is focused on community feedback. So we have 2 presentations from the implementers, as well as I will give, as a participant of the working group, give a presentation on the implementation security update. That is also kind of implementer feedback. We will have a presentation on the symbolic model progress, as well as on the computational model analysis progress. And in terms of the formal status of the working group, so we have a milestone that is set for March 2022 to ship the document to the ISG. So this we will discuss during the next steps. It is not likely to happen right now, as we want to vet the protocol first before shipping it, obviously, to the ISG. And we will discuss this towards the end of the meeting in the next step slots. So that would be all on our side. Stephen, do you have something to complement? No. Okay. So with that, I propose we proceed with the next agenda item, and this is Marko Tiloka giving the report on the hackathon activities.
There's no square standard.
Yes, so Marko, just shout next slide.
Hi everyone, can you hear me? I suppose so. So this is a short report from the hackathon we had the past weekend, mostly on site. Next slide, please. Yeah, the focus was very much on development, I would say, even before testing. And especially Malisha worked a lot on his implementation for Rust Hackspec as part of a bigger project, I understood, to produce something that was verifiable, first of all, and then usable later on also for microcontrollers and other environments. And this was pretty ambitious indeed, and the goal was very specific to produce a runnable implementation, very minimal, especially with the goal to end up with the smallest possible size for the most critical ad hoc message number 2, which is something you can achieve considering the configuration summarized here. So thinking as initiator only, static defilement, and ID cred as KID, specifically integer. Trying to avoid any dependencies and to use hardware acceleration when possible. Next slide, please. Right, the start was not entirely from scratch. Something was available before the hackathon started, especially the hardware abstraction layer in Rust. And of course, the ambition was to cover the very latest version of ad hoc, so the editor's copy to become version 13 of the draft. Well, by the end of the hackathon, everything missing to have something running was actually completed. So the protocol state machine and all the crypto primitives necessary to process ad hoc messages, basically. And this code is now available in the OpenWSM Berkeley GitHub on a dedicated branch. Next slide, please. So with that said, we were also able to do some testing. So Malisha considered is Rust code as initiator role, run against my code for Eclipse Californium as responder. Again, both align with the very latest editor's copy of the specification. And again, we tested the configuration intended for a minimal pair of endpoints. And the result was, fortunately as expected, we indeed could have a confirmation that we produced a message to ad hoc of 45 bytes in size on the wire. And the test was also successful because we both produced the same.
So Marko, could I interrupt you? Could you speak to the mic because we're receiving some...
Oh, better now? Okay. And the test was also successful because we indeed produced the same master secret and salt at the end of the ad hoc execution. Next slide, please. Yeah, we are on the next steps. There are a bunch of few more implementations that are under currently update to catch up with the latest version of the specification. So we expect, especially to those implementations and more, to run more tests in the near future. I think it would be good also to cover a bit more of the traces and possibly the use of message4 and of some error messages out of the ad hoc exchange. As a possible additional site testing, if anyone is interested, there's a separate document in core related to ad hoc that proposes, if you want an optimization, to combine in a single request on the wire the final ad hoc message 3 with the first OSCOR protected request. In case I have that implemented, so I'd be happy to interrupt that little extension too. And that should be it. Thank you.
Thank you, Marco. So just for clarification, so we now have 9 independent implementations available of ad hoc, which includes both constrained for embedded systems and for non-constrained systems. So I think that is important to stress out. And thank you for championing this hackathon activity.
Thank you for the great work.
So I propose, thank you. Are we good with time? Yes. So I propose we continue with the next agenda item, which is the developer feedback. And the first one in the queue is Francisco. So Francisco, can you hear us?
Yeah, I am muted myself.
Okay, so do you want me to pass you the control? I will pass you the control of the slides so that you can switch the slides on your own. So it should be good now. Could you test? Yes,
Yeah,
it seems good. Okay, so the floor is yours.
Okay, thank you. Yeah, so today I'm here to talk about a little bit about our experience with implementing and using ad hoc in highly constrained environments. So just to go through a bit the agenda, first going to go through a bit about the context and the use case that motivated us to work with ad hoc, and our process in writing this ad hoc implementation and using it. And so it was a bit about first looking at what was available, what we could use, what we needed to implement, and then take a look at a bit of some benchmarks and lessons learned during this process. And so our contact was this a cybersecurity research project out of India called IETF, where one of the research axis was around network security. And so some of the use cases that we were looking into there made Lake and Network really relevant for us. And so that's how some of the people in our teams were involved in the working group. And one of these use cases we had in mind was we were looking for a completely different research project into privacy concerns around contact tracing. And we had this use case where we had a couple of contact tracing devices, which were nRF52 BLE devices, which were communicating with a backend server over an untrusted IPv6 over BLE link. And so we were using ad hoc here to establishing a security context or communication channel between the contact tracing server and the devices. And so we were performing a key exchange between these two. And so just to set a bit of context, our goal here was to write a generic implementation of ad hoc that would be able to run on a different series of microcontrollers with quite constrained resources. So we're targeting non-memory allocation. We're not planning to depend on hardware acceleration. So most of the things we're going to see in the presentation are all software only. We wanted to support all authentications, and this was at the time of draft 05 a little bit. So we wanted to target ciphersets 1 to 4, which at the time were mostly P2516 or P256 or C25119 signatures library, for example. There was no afterwards, and no, all the application encryption algorithms were all ISCCM, so there was no CHACH at that time, for example. And we also wanted to focus just on writing ad hoc. So we didn't want to write the crypto libraries ourselves. We didn't want to write the CBOR libraries ourselves or COSI libraries. We wanted to reuse as much as was possible and as many libraries that would most likely be used for our own applications as well, to avoid code duplication. In the end, we wanted to run it all on a series and variety of microcontrollers. Just to reiterate, it was on draft 05, and so while the building blocks are pretty evident, we needed something to CBOR, something for crypto, for key generation, signing, etc. We also needed some interoperability infrastructure in the sense of test vector and interoperability peer, since on the server side, we were not running in a constrained environment, and so it did not make sense, and we probably were not going to run the same ad hoc implementation. And at the end, we needed some ecosystem or something to put it all together. So when we started looking around, there were like a couple of CBOR libraries that we thought we could use, CBOR, Tiny CBOR. Both had their advantages and disadvantages, but they were designed for embedded and had a pretty small footprint and fast executions. When we look at the crypto backends, there's a lot. This in no means an exhaustive list, but this was kind of crypto libraries that for our previous work we already had somehow integrated, so we knew we could use. And the main part here is that like a few libraries were doing everything we needed. The ones that were like WolfSSR or Hackle were not doing it in an embedded friendly way, or did not provide an incremental API, or other reasons that made it not the best choice. And the other ones were not doing everything we needed. So these were our first points to telling us that, okay, we're going to need to actually support probably multiple crypto backends and might want to switch among them. And if you look at this, is just a table that's summarizing some stats on signing, but it already tells us that like when you go looking for some crypto library, it's all going to be about trade-offs. There's none that does everything perfect. And if you're going to want speed, you might be sacrificing some flash and stack. And depending on your use case, you might be okay with sacrificing a couple of kilobytes in RAM to get more speed, and others that's just going to be non-possible. So we have this interest in knowing that we're going to have to use multiple crypto backends and probably abstract them for our own application. And then we needed something to put it all together. And so, for example, there was a lot of options up there like Riot, Zephyr, EmbedOS, Minute, etc. We went with Riot because from our side work, we knew it very well. And so we knew what kind of packages support it has and how we could use it. And there's also some stuff that we identified pretty early or during the process that were missing. So, for example, we would have liked to use cozy abstraction ourselves to avoid then having code duplication in our application side. But sadly, at the time, there was actually no library we could find that we could use because there weren't really any match between all the backends it was supporting and the Cypher suits at the time. So sadly, we had to write our own cozy function, but at the end, that had some side effects on the full application we wrote. And also, although this cozy abstraction or having a cozy library that's basically doing the abstraction of all the crypto libraries underneath for us and providing a more clean interface to all of that was nice. We still realized we were going to need some direct access to crypto for generating keys, hashes, etc. So we couldn't really get a way of going completely around it. On the test vector side, at the time, it was somewhat limited. We didn't have like CBOR certificates, and the certificates we had were not real certificates. Like if we tried to parse them, for example, with an embed TLS X509 library, we would get errors because we got some fields that were missing. And so
Francisco, just let me interrupt you. When you say no real certificates, you want what you mean, I suppose, is that instead of a certificate, there was a dummy byte string presented in the test vector. Okay.
That's it. And on the interrupt side at the time, there was not that too much that we could use. So or not that we were at the time. Everyone was starting to develop them, so we didn't have too much there. And so this is what the end result was. We had this C implementation of Ad hoc called Ad hoc C. There's the link at the bottom, and we used Nano CBOR. Then our default backend was TinyCrypt for all the application authentication and hashing. And for signature, we were using an ECDH. We were mostly using the C519 implementation from Daniel Beer. And for interoperability, well, Timothy that was working with us wrote PyHedOc, which was quite useful for us for testing at the time because, as I tried to emphasize a bit at the start, part of the challenge was actually putting all these crypto blocks together and assembling them. And on the Python side, it was a non-issue, so we could easily cover most of the crypto suits, methods, and parse certificates, regenerated certificates, much easier to then be able to test the C implementation. And as I said, we chose Riot. And just some now I'm going to go into some benchmarks, some stats of like what the result is. And so ROM was around 10K, 9K, and ROM we realized was actually changing a lot depending on the method we were using. So there's two tables here, where one is on method 0, so sign, and 3 is static div Hellman on both sides. And two different colors are two configurations, because we also realized that, well, since we're trying to not do dynamic allocation, you have static buffers everywhere, and since in the different cryptographic stages you are using previous information as cryptographic material, the amount of size you are allocating for additional data or for credentials or for credential ID and ends up being more buffer space you also need to allocate for the eventual transcript, etc. And so tuning these parameters, like for example, just allowing for 1 byte in 1 byte credential ID or whatever, could actually have quite some impact on the actual stack usage of the different message generation and parsing functions. But it was roughly around 4Ks in the worst case with these default configurations. But again, it was very influenced by the size of the maximum allowed size of the credentials or credentials ID or additional data. When you look at the timing that it takes to actually complete a handshake, this is again no hardware acceleration. We run some measurements where we're just taking two nodes, doing some handshakes either over the wire, over 15.4 or BLE, or everything through co-op. And our worst case scenarios were with signature sign or method 0, where between two cortex and 0 was taking up around 20 seconds, while with the best scenario is probably with an M4, where it was taking around 6 to 7 seconds when doing a static Diffie-Hellman authentication method. But if we try to take a bit of a closer look to understand why it's taking so long, it's actually most of it is related to the crypto. And if there's a paper I'm referencing at the bottom, which was studying the sign and verify times that for EED25519, and we can see is basically the overhead is coming from there. If you look at on an M4, for example, verifying a signature of 32 bytes takes around 2 seconds and 800 milliseconds to sign it, and so we're doing this twice in the process, and so we have like a baseline of 6 seconds just from the signing verifying. But again, this is just one library, as I was trying to put in context first. You could also speed it up by changing the library, but maybe you're sacrificing more RAM or more flash usage than your implementation is going to use. Yeah, and so this is a little bit of some numbers, and then we try to integrate it all into our application, and we had a couple of things that we then realized in the field that, sure, initially we decided just to write our own COSE function because it's pretty simple code, but at the end we ended up using COSE libraries in our application code, which ended up having some redundancy. So yeah.
So we have a question. Brandon in the queue. Brandon.
No, I don't. I didn't. So the end result we have so far is that we didn't support. We only supported at the time ciphers to 0 and 1, so there was no P256. But I do have a table somewhere where I'm comparing them, but I didn't do the ad hoc. I don't know if I can. I'll look it up. Let me see. I'll finish and then I'll try to look it up. But it's in the same paper that there's the comparison as well for P256 that I'm referencing in slides 15 or 14. Yeah, and so we also realized, okay, a re-entry API like the one embedded TLS was providing would have actually been quite useful in most of these cases, because the amount of time it was taking to verify or signatures or signing and verifying was actually going over the default quad timeouts we had for our application, so we had to do some special handling for that, and all of this could have maybe been prevented with a re-entry API. And then just some feedback to focus on the implementing the draft itself. So again, this was just draft 5. At the time, it was quite confusing for Timothy, who was developing this, who had the responsibilities of parsing the credentials, how it should be parsed, since from the ad hoc side, how was it supposed to receive the credentials information? This bystring identifier that was trying to save this 1 byte from its point of view seemed to not be worth the extra code complexity that I was actually introducing, and well, now it's been dropped since draft 7, I think. We got some insights on how we could like also toggle RAM to get the best out of it. There's probably some stuff we could have optimized, and maybe have some work buffers, because most of the RAM usage comes from static buffers that are allocated for the key streams, the cozy keys, and stuff like that. And then even though we used CipherSuite 0 at the time, it was mostly because what we had available. We would probably use Cypher 2 or 3. But we could also, if we didn't have something in our application that was already using ISCCM, we might use CipherSuite 5, because at least in Riot, Chachapoli is smaller in size than ISCCM. It's simpler in its implementation, and it's as well easier to implement with an incremental API, which translates roughly into less RAM space that is needed, because you don't have to serialize the same information twice in memory while parsing. And that is it. I'll try to look up the table for the paper where there's the comparison for P256 and ED25419.
Okay, so thank you, Francisco. So we have Brandon in the queue.
Am I in the queue? Yes, you can hear me now. Oh, good.
Yes, yes, we hear you now.
On page 8, I just had a question about the comparison between the different cipher suites. Am I to read this correctly, saying that you don't believe that Mbed TLS supports AES GCM?
I think at the time.
I'm sorry, that is not correct.
Okay.
Mbed TLS absolutely does support AES GCM. And I'm not sure about any of the other X's you have there, but I think it's worth having another look.
Okay.
I thought I should bring that up.
Thank you. Yeah, I'll take a better look.
Okay, thank you, Brandon, for the clarification. Do we have any other questions in the room? No? No? Okay, so thank you, Francisco. I think that is a good overview of, at least of the, that gives us an insight into the performance of the protocol when it is fully implemented in software, when the crypto is fully implemented in software. Those numbers are indeed quite large, but as you said, they are allocated to crypto. So I propose we go ahead with the next agenda item. And this is developer feedback number 2. Marek?
Hello there.
Hold on. So Francisco, can...
All right, can you hear me well?
Yes, so let me just... Francisco, can you pass me back the token? Yes. Developer feedback.
You can skip the first one, probably.
I can skip? Okay, so
Right.
there you go.
Hello, everyone. So my name is Marek. I'm the solution architect within the Asabloy, and focusing primarily on the IoT stack, which we call the modular IoT platform. You can go to the next one. Thanks. So just a super quick overview why I actually been introduced to this challenge is that the company I work for is built upon a number of companies and divisions, and the idea was that every of these divisions are building the stack of their own, and just to unify that, I've been introduced to the challenge to find a stack that can be then shared across multiple companies and multiple divisions. And it's just because it's the numbers and the scenarios that are so large. It's been a hard challenge. And if we can go to the next one, please. So the challenge like we got introduced in was to find a good modular IoT stack that can run on the embedded platforms, also mobile and the cloud. And one of the key challenges and something that we wanted to enable is to device to cloud, device to mobile, and also other way around, and device to device secure end-to-end communication, where we can go over multiple hops with different middle boxes and just keep that, do not break that end-to-end security, just keep it all the way down. So, and to have all of that implemented in the application layer, so we would not have to rely on something within the lower layers. And we wanted to work with formats around the identity like X509 certificates or maybe using CVTs or JVTs. And then all of it to be backed by standards so we can maintain security more efficiently, so we don't have to keep evaluating and just be the only pair of eyes looking at the issue. And you know, we wanted to achieve that with the open source as well. And if we can go to the next one, please. So the areas that I was looking at and we were looking at was more complex than just the communication. So we had to look on the provisioning, so like the generic IoT stack, the provisioning devices with identities, etc., the communication, which is something I will focus on today, and the operations like firmware updates, etc. Next one, please. Right. So the solution we have been evaluating and we have been using so far was based upon CoAP, OSCOR, ad hoc. We use for identities, we primarily focus on the X509 certificates and more. So just to give you a little bit of details on the ad hoc, we are currently on the draft, on the latest draft, so draft 12, and we are compliant with that. Next one, please. Right, so the architecture of the stack looks pretty much like that. So starting from the top, so we have our own RPC protocol that we use, but it's not a requirement, but it's something that we wanted to keep in some of the products. And then going down, for the encryption, we wanted to use OSCOR, like I said. For the key exchange, we focus on using ad hoc. And then we treat, everything was backed by the CoAP. And then on the transport layer, we wanted to, like I said, we wanted to run on the application layer, so we wanted to stay a little bit independent from the transport. So we escaped going on the IP networks only, so we wanted to use the stack in the mobile phone, like device to mobile phone and mobile phone to device examples. So on the BLE side, we just use the standard GATT with services and characteristic communication. On UDP, we use CoAP as intended, and then we also introduce some other transports like serial port in the same way we use BLE. Let's say we wanted to keep like a RX and TX pipe on every protocol that would support that. So on the BLE side, we didn't have any good use case, and we didn't have any good example maybe on how to use the CoAP over BLE. So we went down with leveraging UART protocol over BLE. So one characteristics for read and one characteristics for write. Can go to the next one, please. And then on the just looking on this across the different platforms, we could have, or we did replicate that the whole stack over multiple areas. So on the embedded, we could have achieved the same stack, and then on the tooling side, like the CLI tools, mobile SDKs, we also completed to do that for the cloud as well. And as you can see, we just have a little bit different on the transport backends. So, for example, in the cloud, we also wanted to see if we can fit that use case into existing solutions. So we used the message broker. When in our case was MQTT, we wanted to prove that the communication can run over like just any transport. So I know maybe it's not ideal, but we run it over MQTT. So we had the CoAP running over MQTT just to see how well it can fit into the existing ecosystem, but and just having all the security and the logic within the application layer. Next one, please. Right, so just focusing on the ad hoc libraries. In the previous presentation, there were a few technologies mentioned, which I didn't put in here, but I might as well talk about it. So we wanted to keep the code stack to the minimum and to not have like 6 or 7 different or 5 different ad hoc implementations and OSCOR. So we went with this architecture. So for the embedded part, for the iOS, and for the Node.js, which we use for tooling, we went with the single C library, that is micro OSCOR, micro ad hoc library. So each of these free components, like on the embedded iOS and Node.js, are just the wrappers or just wrapping the native C library. So on the Node.js, we have a native module. On iOS, we're wrapping the C component with Objective-C and then using in Swift. And then on embedded, we just use Oscar Micro Edoc directly. And yes, we have, as a backend, we have used embed TLS, which I can confirm on the previous node on the AES that it worked. But we use embed TLS on NRF. On the embedded part, we use embed TLS version from Nordic Semiconductor that is hardware accelerated version. So we got the full hardware acceleration on that, which are some numbers I'm going to talk about in a sec. And then for Android and cloud, we have our own Edoc implementation that for now we keep internal, but that might change in the future. And just on the top, you can see that we try to keep these APIs very easy to use and just with the minimum input from the user. Next one. Right, so just to give you some details on our Edoc use case, we are focusing just for now, we are just focusing on Edoc usage with the certificates. And then, so we have CAs on both ends. So we have a responder root certificate on the initiator side, and initiator root certificate on the responder side. And then for the credentials, we use full X509 certificate, which we then validate. So we go with, our certificates use P256 curve. So we go with the method 0 with signatures and suit number 2. Right. Okay, so just on the embedded platform, like I mentioned, we use NRF 52840 with the free RTOS. That's maybe not a main or master free RTOS version, but we have our own modified version a little bit. For the co-op, we use Lobaro co-op library, and then Microscope Micro Edoc, and then for crypto, we use embed TLS that is hardware backed. And we have that platform that you can see here, but all in all, we just, as a main, we're running this on the standard NRF 52840 dev kit. Next one, please. Right, and a little bit about the performance. So this is a screenshot from the Node.js 2 that we use, and that communication here was running over BLE, over standard GATT. So we have our own dongle, like a Zephyr dongle, Zephyr firmware dongle, acting as a BLE dongle that is running over UART. So Node.js tools over UART over standard HCI command will communicate with that board, and then we'll in the Node.js library we have like full BLE API to back it up. It's actually based on the open source Nobu library. And then this screenshot shows Node.js 2 being an initiator communicating with the responder that is running on NRF 52840 with our RPC protocol on top of it. And as you can see, like what we do here is we do scan for BLE, we connect, we discover GATT, we perform the Edoc, like I said, with the credentials using certificates on both ends with the method 0 and suit number 2, and then on top of that we do OSCORE, and then we set up our own RPC command, and then all of that is taking less than a second. So just for the Edoc to complete without the initiating of the RPC layer is about 700, 800 milliseconds for everything that I said, together with the validating full validation of X509 certificate.
Just for my understanding and the clarification, 595 milliseconds, what does it refer to?
Okay, so that's the first number. So the first number is where we connected over, scanned the BLE, connected over BLE, discovered GATT, and sent message 1.
Okay, so kind of BLE.
Yeah, let's say set up with the first initial message being sent.
Okay, and 770 is the actual ad hoc handshake.
And that's the total time from the start.
Oh, so that's included in the. Yeah. So, okay.
So just between message 1 and the full ad hoc, it's been, let's say, 180 milliseconds.
Okay, so we have a question from Michael.
Yeah.
Maybe Melissa, Michael Richardson here. Maybe Melissa just asked the same question and I didn't understand the question the same way. So Bluetooth has a encryption layer, and GATT avoids it, or yes, okay. So you're going clear. Your ad hoc messages would in sense be in clear over Bluetooth.
Yes.
Okay. Just want to make sure I understand that.
Yeah.
That's really cool.
Yeah.
Okay.
So ad hoc over bare metal Bluetooth, kind of.
Exactly.
Okay, yeah, pretty cool. And the total, so all of that takes 770 milliseconds.
Yeah. Obviously, I chose the best one. I had ones that
So-
are running for 800 something, but for the screenshot wise, I choose the 700 milliseconds. But yeah, roughly, we always stay around 800 milliseconds.
Yeah, so-
and that's important to know that this is, there's also UART delay because the bridge is communicating over, the BLE bridge is also running over UART. So there's always going to be a few milliseconds here and there of a delay. Right, next one, please. And this is the same or similar results, but happening directly from the mobile phone. It's exactly the same process. So like I described before, so scanning, connecting, discover GAT, certificate exchange with the certificate validation. And what we validate for is, just so you know, we validate against the root certificate, and then we validate the expiration time. For now, that's the only certificate validation that we do. And then on the mobile side, avoiding this UART part, like with the tooling side, we get results in 600, 700 millisecond range. Next one, please. Right, so for the future, for now, we would really focus on, we want to build now a co-op HTTP to co-op proxy for our cloud infrastructure. That's also going to be backed and working with the EDOC and OSCORE. And we're going to try to stay as much as compliant to the co-op, HTTP co-op proxy specs. We have some things that we are not sure yet, but with those things, we hopefully can contribute back to the specs and also the open source, which we already do. For example, for the micro-OSCORE, micro-EDOC library, we have been working first with the Fraunhofer and then with the author Stefan now to also be included as the collaborators on the C library.
So just as a clarification, the mu ad hoc and mu OSCORE implementations were presented during one of the past meetings by Stefan here,
Okay.
and he presented the findings of his paper that includes these benchmarks.
Yeah.
But yep.
So yes, so we work with Stefan on that as well, and then more on the personal activity. I was working with Goran on the latest test vectors for the traces, and my contribution that's going to be that I hopefully will get up in soon is to build a better test vector or more modern test vector generator. The current one that we have is not the best one, and it requires some more love.
I suppose we will discuss this during the traces draft discussion together with all the updates on the traces. Yes. Okay.
Perfect. All right,
Okay.
and I think that was the last one, if I'm correct. Yes.
There's
So,
thank you.
thank you very much.
Yes. So do we have any questions for Marek? I see no one joining the queue, so thank you, Marek, for agreeing to present today, for giving the feedback to the working group. It is encouraging to see the protocol being used in the wild, prepared to be used in the wild.
And thanks to everybody for staying on time. So I hope I don't have to clamp down on the next presenter. Who is that?
So yes, but before we go to the next presenter, I would just like to bring the comment by Francisco to the mic, where he confirmed that on the slide set of developer feedback number 1, there was a mistake in the embed TLS column, where all the rows should have been checked. Including the ASCCM primitive, which was shown as not supported. So Francisco confirms that. This was discussed in the chat.
Just one more comment there. I think the Edward curve support is kind of in PRs and not there yet, but you can get it from Embed. Just wanted to add that.
So just for clarification, we're still talking about embed TLS and the support for X25 for curve 25509.
The EDDSA is kind of, from what I see, it's PRs, and it's towards this year that it should be fully integrated. But there's already, you can already use it.
I didn't quite capture that. Maybe if you can restate.
Sorry, there's in the in the table I had like some checks with with an asterisk, and those mean that it's not in the master branch, but there's PRs or somewhere that's implemented and you can use it. And for ED25519, that should also be the case for embed TLS.
Okay, so just maybe as an action point, Francisco, if you can take to update that slide that contains the error that we can upload to the data tracker and have correct record in the IETF. Is that okay for you?
Yes, we'll do so.
Okay, thank you. Okay, maybe it's better if you share.
Well,
So
yeah.
no, but you need to click to press the buttons.
Oh, you want to stand up? Okay,
Yeah.
sure. Which one are you? Implementation security.
Okay, so hello everyone with my chair hat off this time. So, next slide, please. So to give you some context about this presentation, as you know, as we all know, as we all know, Lake as a working group targets constrained environments, and constrained environments in our context mean embedded systems. So many of our implementations will be executed on embedded systems. And you're probably all aware that the embedded programming language today is dominantly C, and C is memory unsafe, and C doesn't play well with security. So what we standardize here is obviously crucial to security of the protocol, but what ends up in the wild is as important, and the protocol in the wild will be as secure as its implementation is. So the goal of the work we've done was to produce an implementation that has some security properties, such as provable correctness of the implementation with respect to a given model, provable memory safety, and side channel resistance to considering the threat model where the device itself is not completely trusted. So a team from INRIA in Paris called Prosecco developed a framework called Hackspec that is a framework for verification of different implementations that essentially for the generation of verified implementations. And next slide, please. This framework is called Hackspec. So it's called Hackspec, and the specification language is a subset of Rust. So what that means is that when you write your model, your specification, you are essentially writing Rust code. And since you are writing the Rust code, this means that what you write, the model, the formal verification model, is no longer some mathematical abstraction of the protocol. It is executable code. And this specification enables the generation of verified implementations, which means that it is possible to generate a formally vetted implementation satisfying those security properties from this model. And this team from INRIA has developed a complete framework to type check this Rust specification and to enable its compilation onto different mathematical abstracting languages such as F-star, Coq, and essentially it can be also executable. Next slide, please. So in practice, what that means is that to arrive at an implementation that is formally vetted, we need to implement some code in Rust, in a subset of Rust called Hackspec, and then by using their framework to generate to generate the F-star model, which is this mathematically abstracted language of the protocol that allows the verification of different properties of the protocol against the model. So once you arrive to that F-star model, you can essentially prove the different properties such as symbolic security on the protocol in an automatic manner. So from F-star model, which is step number 2 in this procedure here, we go, what is necessary is to write and verify the implementation in another language called the Lowstar against this F-star model that was generated automatically. And from there on, there is automatic set of tools to compile this Lowstar code to verified C or verified Rust code, satisfying those properties that we wanted to prove from the very beginning. So you can see this kind of flow on the right. And I'm trying kind of to abstract it for you. And I'm focusing mainly personally on step number 1, where we are implementing this specification that is the model that is going to be compiled to the F-star model. Next slide, please. So the goals of the implementation are twofold. It needs to be verifiable, but in the same time, it targets as Lake, targets constrained environments, and it needs to be executable on microcontrollers. So in my mind, that means minimal implementation, minimal, very lightweight implementation of the protocol, where we are not pulling in a bunch of different libraries and dependencies, and we are keeping the memory footprint and the code footprint to its minimum. As we've seen from the previous presentations, software execution of different cryptographic libraries takes a lot of time, and we've seen from Francisco's presentation that it can take up to 10 to 15 seconds to complete the handshake due to the execution of crypto on different microcontrollers in software. We want to rely on hardware accelerated crypto. So our initial compilation targets are essentially native to facilitate development, but then also CC2538 board from Texas Instruments and this Nordic chip that both support acceleration of the different ad hoc cipher suites. Next slide, please. So we encountered a couple of challenges on this path, and the main one is that we said we want a verifiable implementation, but the problem is that this framework that Prosecco from INRIA developed, it relies on Rust standard library and cannot be compiled in a no standard environment, meaning that it's at the moment not possible to produce an executable for microcontrollers. Second point, which is kind of a feedback for the, well, not really a feedback, but it's mostly a point to be aware of, is that during this work of implementing the protocol, majority of my time was spent on figuring out not the support, but getting around the point compression not being supported in the libraries. Point compression meaning that the elliptic curves, the point on an elliptic curve is typically represented with X and Y coordinates. In a compact representation, you will transfer, as we use in ad hoc, we transfer only the X coordinate, and you're supposed on the constraint device in the implementation to calculate the Y coordinate on the fly. And this is poorly supported with the existing libraries, including the one that Hackspec uses. So a lot of my time during the implementation actually was spent on that. And finally, in Rust, since Rust is, there is an ongoing initiative on porting Rust to the different popular hardware, embedded systems. For some boards that I outlined, namely for TI's CC2538 board, the support is still lacking, so we are kind of developing it on the fly. Next slide, please. So the current status of the implementation is that we progressed this during the hackathon quite a bit. We came into the hackathon, as Marco outlined, with a minimal implementation that passes the test vectors, different essentially unit functions, and we came out with a fully fledged minimal implementation that interoperates with the Java-based backend that was used for interop testing. So this minimal implementation means the initiator in static mode with CCS and with integer kits, essentially instantiating the 45-byte handshake, 45-byte message of the ad hoc handshake. And what is important here to outline is that the implementation essentially uses 0 external libraries. All the CBOR and COSI encoding are done inline. And it's completely no STD style developed. So as I said, the status is that the implementation passes the test vectors on a native machine for now, successfully interrupt with the Californium ad hoc, and we are currently working on the build support for different boards that I outlined. Next slide, please. So we have a couple of open questions that we want to bring up and discuss with the formal analysis community. And this is mainly related, how can we ensure that this model that we write is really bound to the specification, because this is the one big assumption that the academic community makes when modeling the protocol and when verifying the implementations. So essentially they're making the assumption that the model, so in this case this Rust code that we write, is a perfect, or I would say ideal, representation of the RFC. So, and this is very open question how we ensure that. So this is something we will take as an action point to discuss with the formal analysis community and mainly the Prosecco team. And in terms of the implementation, the next steps are essentially to complete the port to these two boards and to publish this as a crate on crates.io to be available to the people in open source. And once that is done, we have our formal model that we need to use to formally prove to generate formally vetted code that can be executable on a microcontroller. So I think that is my last slide. Yes, so here are the people that helped out during the development of this in alphabetic order. So this is Christian here, also Kartik, Franciscus, Denis, and Marco, during the hackathon and during the sprint during the previous period. So are there any questions?
No?
No? Okay.
Thank you. Computational model analysis.
Okay, with that, I propose we go with the next agenda item, and this is the computational analysis of the ad hoc protocol. And Baptiste, can you hear us?
Yes, I can hear you.
Okay, yes, so we hear you loud and clear. So the floor is yours.
Okay, so hi everyone. So I will present you the how we will prove the security of the ad hoc protocol in the computational model. So first, the differences between the symbolic and the computational security. So in computational security, we consider the messages as bit strings rather than terms, and the primitive are simply functions on bit strings. In the computational model, the attacker is any probabilistic polynomial time algorithm, and the goal of the attacker will be to learn any bit of information on the bit strings. So where in symbolic security the attacker cannot distinguish when the value of the secret changes, in the computational security we have to prove that an attacker cannot distinguish between a secret key and a random value. So a bit of context. So we have the constraints of EDOC. So small number of messages, small message size, and minimize code and memory footprint. So this constraint leads to the use of in some leads to use 64-bit security MAC and 128-bit security elliptic curves diffie-Hellman. And so
just
the
as a
idea is,
clarification, Baptiste, sorry for interrupting you. So just as a clarification, so this is one particular mode of ad hoc and
Yes.
static, and obviously the most constrained setting, the cipher suite 0 and 2, which use the 8-byte max.
That's it. So the idea is to prove that even using a 64-bit security MAC, we have no leak of security. So our security goals. So first we have to define what is a security level of 168 bits. So we have to consider the execution time of the protocol and the success probability of the attack. So the success probability for the attacker to distinguish between the session key and a random value. So with T, the execution time of the protocol, and epsilon, the success probability, we have to prove that T on epsilon is at least greater than 2 to the 128. So if we reach this, we can say that we have a security level of 128 bits. So we have 3 points to prove. So first, we have the key privacy. So at most, both participants know the final session key. So by compromising the long-term credential of SRP, an attacker should not be able to compute past session keys. So this is a forward security. So even even if an attacker gets the information much later, he cannot take older session keys and get information about it. Then we have the mutual authentication, where exactly both participants have the material to compute the final session key. And we have to prove the identity protection. So for the key privacy, so that's also known as implicit authentication. So it relies on the computational Diffie-Hellman assumptions, and therefore it depends on the group side in which we are working. And to prove the key privacy, we will use the find then guess model, where we give the adversary the access to 3 oracles. So the first one is the send, where the attacker can model where the send oracle models an active attack in which the adversary may intercept the message. You can modify it, create a new one, and you can do whatever you want. The reveal oracle, which models the misuse of the session keys by a user. And finally, the test oracle, which tries to capture the adversary ability or inability to tell apart a real session key from a random one. So the idea is that given an infinite access to the send and reveal oracles, and only one access to the test oracle, the attacker have to. We say that attackers succeed if he cannot distinguish the session key from a random value. So the idea here is to that we will consider the attacker that can use as many times the send and reveal oracles, when he will think that when you think he can say that the key is either a valid key or a non-value, he use the test oracle, and then he wins if its guess is the good one. So the mutual authentication, so that's equivalent to the explicit authentication. So we use flags to represent the mutual authentication. So you have two flags. The first flag, so both initialized as at 0, is the flag accept. So either the initiator of the responder will put the accept flag at 1 when he has the required material. And we have the terminate flag that asserts that the other participant has the required material. So when the idea is to prove that both participants can activate the terminate flag with the required security. And here it relies on the MAC security. So as said before, as we use 64 bits MAC, so there is a mistake. So 64 bits MAC provide 64 bits security. And as we want to prove that we have a 128-bit security, we will check if the 128-bit security is reached after few messages, because the idea is we know that with a simple execution we will have a 64-bit security, but we want to check if after 4-6 messages, so we have other information that will allow us to guarantee to prove the mutual authentication.
Okay, so just as a clarification, in the requirements document, we have agreed upon the security level of 127 bits, and we do include 8-byte max in the protocol. So what Baptiste is referring to is that the 128 security bits that they are studying, if I understand correctly, Baptiste, please correct me, that you are studying that after a few application messages that are exchanged, we can actually reach the 127-bit security over the given key, even though the max that were used to authenticate the handshake were only 8 bytes. Is that correct?
It's perfectly correct. So that's it. So that's the goal. Thanks for the clarification. And the third point is the identity protection. So by definition, we have the identity protection if the protocol is secure against active attackers for the initiator and against passive attackers for the responder. And we will represent the security by using games. So we will give the attacker two identities, and an active attacker should not be able to say which one is the initiator. And for the responder, so also we will give two identities. One of them will be the responder, but a passive attacker should not be able to distinguish which one is the responder. And to conclude, we have the protocol decomposition. So in yellow, we have the data used for the key privacy. So that are the Diffie-Hellman public keys and the mutual authentication will be have the value in with the value in green, and the identity protection is ensured by the encryption. So the idea is to study each of these values for the required security concerns, and prove that the security is as expected 127 bits, or say that using a Mac with 8 bytes is not doable. So this is the end. So if you have questions.
Okay, thank you, Baptiste. So I believe we have Scott in the queue.
Okay. Yeah, okay. Can you hear me?
Yes, we hear you.
Yeah. Excuse me for not following this real closely, but I believe what you're doing is saying you'll exchange several messages using a 64-bit Mac, and and if all those messages authenticate, then you hope to get the full 127-bit security level. Is that correct?
Yes.
I don't believe GCM gives you that property because if the attacker finds the initial message and manages to forge it, how he performs a forgery will tell him how to perform later forgeries with essentially no additional effort. So you only get 64-bit security.
I can't tell you more because you want to determine if yes or not. But the idea is maybe to be able to say that we do not have the security before the attacker can forge a value. So I don't know if it answers your question.
This is not a question. This is an observation based on the security properties that GCM gives you. This is specific to GCM. Your other authentication, your integrity program routines functions do not have the same property.
Yes, the idea we so yes, the idea is more that we know we will have 64-bit on forgery, but yes, I don't know how to say that. Maybe that's more being able to detect an imposter before he has the time to forge the Mac.
What attacker would do is have to guess right for the very first one.
So I didn't hear well. There is an echo.
Okay. What the attacker will have to do is basically do a correct guess on the very first Mac he's attacking. Basically doing a blind guess. Actually, he can do a little better than that, but not much. Once he's done that, then and he's done that successfully, then he can actually do later for more forgeries for essentially for free.
So I don't hear you well. There's an echo. I don't know if you can repeat, please.
Okay. If the attacker basically for the first message he wants to forge, he does essentially a blind guess. Mm-hmm. Once he's done that, and if he's successful, then he can forge later messages, which means that the security of the later messages of those Macs does not increase the security level. Therefore, you're stuck at 64 bits.
Mm-hmm. Yes, that's interesting. Maybe
so just in the interest of time, Scott, is the kind of attack you're mentioning specific to GCM, or would it also apply
Yes,
to
it is.
CCM?
No, it is specific to GCM.
So I don't believe we have 64-bit GCM Macs in the protocol.
Oh, you do not? Okay, good for you. Thank you very much.
Okay, great, thanks. So Mark, and if we could kind of move on time-wise, be great. So Mark, go ahead. Mark, you're in the queue. Mark Alunga. I guess not. Okay, in that case, Baptiste, thank you. I guess you were wondering about the time. Go ahead.
Yes, so Mark has again asked to send screen. Mark, can you hear us?
We're not getting audio from you.
We're not getting audio, so we'll have to cut it here. Oh yeah, we cannot hear you. We see you, but we cannot hear you.
Can you hear me now?
Yes, now we can hear you.
Oh, I apologize. Microphone problems. I just have a question for Baptiste. Thank you for the presentation. So I'm from ETH Zurich, where we have a team also working on the computational analysis. So this presentation is of interest to us. We're just wondering, in your analysis, when you were talking about key secrecy, what did you define actually as a session key for the protocol? I was wondering whether you could give some details on that, or maybe if someone else as well could jump on that to give a bit some more details, since we're a bit confused on what should be considered as a final session key for EDOC. Thank you.
So the final session key is the key that the common key that both participants share. So that's the how to say that. Yes, that's the key they share at the end of the protocol. So I don't know if it's clear.
So I believe you're referring to PRK4X3M?
Yes, in a sense, yes. So essentially, in as far as we've been in the analysis, we're not able to really clearly say, is the peer key considered as sort of the final session key, or whether there should actually be some sort of final derivation as well to actually extract what should be the session key.
So maybe the authors can respond to that. If not, I can also complement. So, Joran, would you like to comment on this, or?
Yeah, I think we should actually take the next presentation because they have a proposal. But yes, it should be either PRK, X4, X3M, or derivation. The presentation is actually addressing this.
So it's cutting on your side, Joran, so I hope that will be fixed. It seems like a bandwidth issue.
Yeah, I think what is session key, it might be different from the formal analysis where you need to define the concept of a session key, and then what is actually used in ad hoc, where we do derive different session keys for example, OSCOR, but that may or may not be covered in the formal analysis. But I think maybe we need to come back to that.
Yeah, let's put it there.
But this is,
I know.
yeah. Okay, so we'll have to cut it here. So I propose we take this to the mailing list, as this is crucial for the security of the protocol and for the work of this working group. So Mark, thank you for letting us know that you work on this as well. I have a final question for Baptiste on the timeline of his work. So Baptiste, could you comment on the timeline? When do you expect to? Because from my understanding, this is the work that has started but is not kind of completed yet. So could you comment on the timeline?
Yes, so normally I guess it would not require so much time, so I have to check with David, but I think yes, 2 months will be enough to conclude the security analysis.
Okay. Okay. Thank you. So essentially, we should hear back from you for the next IETF meeting then, which is end of July in Philadelphia. We should have more results. Okay, so I propose we go ahead with the next agenda item, and this is Charlie. Charlie, we see you. Can you hear us? We don't hear you still.
Yes.
Yeah, there you go. So the floor is yours.
Okay. So hi everybody, I'm Charlie, and I'm here to describe at hopefully a high level the bit of research we've done on Lake EDHOC protocol. So first, a brief introduction to the techniques we've been using for this analysis. And we've mainly been using a platform that essentially we can define, we can write down protocols inside some kind of high-level programming language, where you have a way to abstract the inputs and the output over the networks. And then from this specification, this high-level specification, we can ask automated tools to verify some security properties. And we can typically use ProVerif or Tamarin that have been used previously in quite a lot of protocol analysis to tell us, is the protocol secure, is the protocol secure, or is there an attack? So maybe the single technical slide will be this one, which is just to give you a taste of what it looks like, essentially, how we model things. And what we do is we abstract the function computations by simply specifying which property they should satisfy. So typically to declare decryption and encryption, we're going to give this definition that decryption of encryption gives back the plain text, essentially. And we're just going to define positively the kind of properties verified by the computation. And this will be enough to verify security or fine attacks. And we can define properties in a very generic way, which is essentially event-based and time-based. So we can ask, for instance, so what you're seeing at the bottom of the slide is some authentication property, where we're saying that whenever R accept with some parameters, typically a PKI, a public key for the initiator, which corresponds to some honest PKI, then it implies that somewhere in the past, the initiator did accept. So we can specify a lot of properties like that, secrecy and everything we want to check essentially on Lake. What we've done, which is a bit different from other works in our models, is that we're trying to push a bit further the modelings to capture a lot of small, sometimes unexpected behaviors of the primitives that are not taken into account. So typically for Diffie-Hellman, you have an identity element that whenever you're going to exponent it, it's going to fall back to the identity element. But you also have low order points that can easily create collisions between exponentiated values, for instance. Or signatures typically can have malleability, or you can also generate some yes keys, public keys that will always validate against all messages. And typically, hash functions like SHA-256 have, well, based on the Merkle-Damgard construction, length extensions. And also some kind of, and we can consider many subtle weaknesses of hash functions that already exist typically for MD5 and SHA-1, that's present prefix collisions, and that will maybe one day will exist on SHA-256, and we try to be prepared if they arrive. So our model, more concretely, includes the 4 methods of authentication that can be fully executed in parallel. We include a trust and first use paradigm for the public key infrastructure. We model compromission of long-term authentication keys, session keys, ephemeral shares, so everything. We also modeled the post-quantum variant, so for the alternative model with the chem-based variant. What we're lacking currently is a fine-grained modeling of the cipher suite negotiation, which is a bit complicated to abstract, so that's still not done. And we don't have the optional false message as well as the rekeying, the key update mechanism that follows. And so on this model, we used Tamarin, Proverif, and the tools to obtain this kind of results. So this is just to give you a high-level idea of what we can get, where essentially we check each of the property on the left-hand side in different threat models. And what's interesting is that in the, let's say, most reasonable basic threat model, everything works as expected. So that's pretty nice for the protocol. But when we can start to consider a stronger threat model that will occur less often, that are less likely to happen, but that can still be realistic and interesting, we start to find some flaws in the protocol, and I will describe those in more details. But yeah, based on this big table, essentially, the high-level feedback is that the protocol provides all expected security properties in many reasonable threat models, but when we go to stronger attackers, there are some maybe improvements to be made, and so we want to propose 3 different essentially class of improvements that ideally won't increase the cost of computation or anything, but still avoid potential misuse of the current design, strengthen the trusted execution environment implementation, and ideally also improve the future resilience of the protocol. So I'm not gonna describe quickly those 3 points, but for the details on everything, we'll be sending out mails on the mailing list with concrete proposals to make it straightforward. So talking about potential misuse, and it actually ties back to the discussion that was happening at the end of the previous talk. What we call the session key, so PRK for X3M, actually offers weaker properties in terms of security than the exported keys. Typically because if we have a dishonest, if we're talking to a dishonest responder, they may have a lot of control over the final value of this PRK. For instance, because they will send us the identity DH element, or in the post-quantum setting, through an encapsulation, the attacker can have full control, actually, of the PRK for X3M key. And also, compared to the exported session keys, this session key is not linked to the execution of the protocol, and typically does not authenticate TH4. And so typically, an implementer may decide currently from the standard to use different key exporters than the one specified, actually. And if they do and do not include TH4 inside the key which is used, then you can break the authentication of TH4 because the key confirmation essentially of PRK for X3M won't authenticate TH4, of course, and even computing successfully the exchange because typically AES CCM is kind of malleable. So in the formal sense, you have the integrity of the plain text, but not of the ciphertext. You can break the authenticity of TH4. So essentially, it looks like to us the protocol will benefit from a clarified, essentially final key. What is precisely the session key, which would be the equivalent of the master secret in TLS. And so typically, adding a final key derivation where we tie together PRK, the PRK and the transcript will produce a final key with the best possible guarantees, essentially. And typically, this would allow, by the way, as some kind of optimization to remove the TH4 from the stored material and the exporter in later times, essentially. A second potential misuse of the design So it's a bit subtle. It's kind of hidden in the appendices, but it's about DDoS resilience. One issue is when the standard specifies that an implementation could store the protocol state to be able to recompute and resend the last message. There's actually an issue with that for the third message, because whenever we use AEADs, it's very important in terms of cryptographic guarantees to never use the same key and the same IV for two distinct messages. And well, at the step of the third message, if you store the state used to compute this this message, if the signature is randomized, which is the case for some of the schemes proposed here, what you're going to do is compute two different messages because the signatures are randomized, and you're going to use the IED scheme with the same IV and key for both of those different messages, and thus it falls outside of the classical use of IED schemes. So here the suggestion is simple. We should just forbid this state storing, and just simply, if you want to resend message, you need to resend exactly the same, essentially. Another point we touched at is it looks like the trusted execution environment implementation could be strengthened. Sorry, because essentially, so this is a very strong threat model, but let's assume that all the authentication operations are put inside a trusted execution environment. So essentially, either the long-term signing key or the long-term defilement share are stored inside a trusted execution environment, and we assume that otherwise the device is compromised. So what we would expect, essentially in this case, is that we don't have any secrecy, of course, but we would want to still have authentication. And so concretely, it means that we leak the initiator ephemeral key at the beginning, and we also leak the session key at the end, but we don't give us access to authentication keys. So here there's actually an in-person attack, which is, so I don't think I'm going to go through it in details, but once you've seen it, it's actually quite straightforward. It's in the static authentication mode, where the idea is that actually the MAC key and the session key are exactly the same thing. They are the same value. So if you leak at the end the session key, you are leaking the MAC key, and then the attacker can, using this MAC key, use it to produce other MACs than the one expected, and you can lie to a responder, essentially. And thus, essentially in the static authentication mode, trusted execution environment implementation doesn't really make sense. And it's to note that it's not the case in method 0, where you can do everything nicely. And the secret key, if you store the secret key for the signatures inside the TE, you don't have this issue. So there are a bit two things here, which is one, the static authentication method is, in terms of TE implementation, slightly weaker than method 0. And we need to think, if we want to propose TE implementations, we need to find a way to make those things better. So there may be possibilities, but it's quite, it's still a question of how to propose the best interface for people that will want to use TE. And finally, the last point, which is about, so what about 10 years or 20 years from now, will EDOC be still secure? Essentially, what we want to look at are chosen prefix collisions. So as I said, for MD5 and SHA-1, those things actually exist. And for SHA-2, not yet. And maybe never, maybe in 10 years they exist. So ideally, it would be cool if we don't have those, if these kind of things don't lead to attacks on the protocol. And so we have a threat model where essentially the attacker, given two prefixes, P1 and P2, can compute two big bit strings, C1 and C2, such that the attacker creates a collision between the hash of P1 concatenated with C1 and the hash of P2 concatenated with C2. And using these kind of collisions and the fact that the protocol agents may access the identity element, we can essentially create a machine in the middle attack, essentially, where the attacker is going to be able to break the secrecy of the protocol, and also actually lead to downgrade attacks, where the participants won't agree on which cipher suit they should use, and so the attacker can actually weaken the cipher suit. It's actually quite simple to mitigate this thing. And typically, so checking for lower order groups or at least the identity element. And this kind of attacks typically exploits the fact, well, you need to stuff a lot of bits that correspond to the collision bits inside the transcript to be able to create the collisions. So it actually exploits a lot the fact that you have those external authenticated data, as well as the identifier CI and CR. So it could be mentioned that depending on the length of those values, it may weaken the protocol in a sense. And it's actually quite important for a lot of the specification of message processing. It's actually quite important that there is some kind of typing going on. And if an element that you receive on the network is not of the expected type, typically the suits are supposed to be arrays of integers. And if in the middle of this you encounter a bit string, you should reject these kind of things. And so maybe the standard could also be clear on these kind of things and more strict in a sense, or say that if you don't, bad things may happen. So to conclude this overview, well, on the long term, we first want to improve and deepen the analysis, so typically to include the key update and the first message. We plan to keep the models up to date. So whenever the draft evolve, our plan is to keep the model up to date, yeah? And this all the way up to the final RFC. So if all goes well, when the protocol goes out in the wild, there should be formal verification of the actual standard. And maybe we will also look at the computational security inside a proof assistant. And that's it for me.
Thank you, Charlie. So do we have any questions for Charlie? So there was a comment by Christian, but okay, so he will bring it to the mailing list about future-proofing this, I suppose. So since we don't have any questions, yeah, we can only thank you for doing this work. This is really great. I propose as an action item for the authors to convert this list of remarks into GitHub issues, and that we start with discussing those one by one on GitHub and on the mailing list where necessary. And this would be our typical working process in the working group. But other than that, I think, again, this is great. Thank you so much for doing this work. And just maybe could you comment, could you comment on your future plans regarding this work? Because the protocol is still not completely, we might publish new versions. Do you plan on updating this model that you did, and do you plan to stick around?
Definitely. So at least on my side, I want to commit on that. Hopefully I can bring my co-authors in also. But yeah, I want to keep working on this project, definitely.
Okay, that's great. And one last question is, I suppose you plan on publishing this in some venue in this work? Yes. So please keep us informed, the working group or us, the chairs, and we can forward to the working group about any publication that results from this work.
Okay.
Yes. So with that, I would like to conclude the slot on the formal analysis. And again, I cannot emphasize this enough, how important this work by Baptiste and by Charlie and his team is important for the working group. And I believe I speak on behalf of the whole working group when I really thank you for doing this. and also I invite Mark, who we have just came to be. We just realized that there is another activity going on that we're kind of not aware of. To reach out to the Lake chairs or the Lake at IETF mailing list to let us know about the plan and the activities, such that we can synchronize the activities for and presentations for the next IETF meeting. So with that, I propose we go to the next agenda item, which is our chartered items, which are typically at the beginning, but because of the nature of this meeting, we've put them at the very end. So, Joran, can you hear us?
Yes, I hear you well. Do you hear me?
Yes, we hear you well. We hear you well. We're just about to share your slides.
Thank you.
Yes, that's the one. Yes, that's the one. Okay, so there you go. The floor is yours.
Yep,
so I propose to keep it down to like 11 minutes, and
11 minutes.
such that we have time for next steps, to discuss the next steps.
Sure. Okay. So I'll be quick. These are the this is about both the drafts that we're working on. Next slide, please. Next slide, please.
Oh, you have control.
Oh, I have control. Fantastic. Sorry, I actually don't know how to change slides. Should I share myself?
Maybe I need to do it again.
I don't see any controls for the slides. Sorry, now I found it. No worries. Okay, so since this will be talking about the ad hoc draft and the trace list draft, those are the two drafts. And there has been, on the terms of publications, there has been no changes because we have still the old versions, but we have been progressing these on the GitHub. And what we've done is mainly finishing off the 5 reviews and updating based on all those comments. And that's completed now. We don't have any old issues. All issues are essentially related to test vectors. So this will be going through the changes that we made since version 12. First, the ad hoc document. And the main changes are an update to section 3.5, which is the section on authentication. It's an update to section 3.8, which is the external authorization data. It's an update to processing following the changes in 3.5 and 3.8. And it's an update on the compliance requirements, which is on the next slide. And a little bit more on the details. So section 3.5 was about, or still is about, authentication keys, authentication credentials, identification and credentials, etc. One request was to shorten this section. And there were also specific comments about what kind of verifications, authentication operations that was performed. The change we've made is that we have now split the content into section 3.5 and a new appendix D, where section 3.5 contains the core protocol operations, the proof of possession, transfer of credential info, and appendix D contains all other authentication related operations like certificate chain validation, identity verification, and so on. And similarly, in section 3.8, we also split the content into what are the expectations on the external authorization data, and that specification of the EAD value, and that's part of the body now, whereas the new appendix E contains examples like we talked about in the previous IETF meeting. So we hope this is making more clear what is part of the core protocol and what is outside the protocol. Things that sort of relate to the protocol but are not strictly part of the specification. And the update to processing was also to handle accordingly what the things that relate to the core protocol is stays in the processing, and the things that are not in the core protocol is taken out. So I think that summarizes the main changes, except for the compliance requirements, which is on the next slide. So we've had for a long time a discussion about what are the mandatory to implement cipher suites and other related compliance requirements. And this, we had a couple of interims, and in the last interim we concluded on this formulation. So implementations must support cipher suite 2 and 3, but we also have a general precondition saying that in the absence of an application profile specifying otherwise. So that's what we have agreed on on the mailing list and following this interim discussion. So it wasn't something everyone was super happy over, but this was basically something that everyone seemed to be able to live with. And there is another update on the compliance requirements related to padding, and we have now introduced the must be able to parse padded messages. So it's the ability to handle plain text, sort of to hide the length of the plain text. You must be able to parse padded messages, but not all use cases need to actually use this. So the must is on the receiving side, not on the sending side. And those were the changes to the compliance requirements. I'm rushing ahead now. Stop me if there are any particular questions. The other updates made on the ad hoc document are sort of more editorial and clarifying. The error handling is clarified. There's a renamed error code. There is a clarification of cipher suite negotiation. There are also a one breaking change here in the terms with respect to the exporter label. So we have reduced the number of characters in the exporter label to avoid an additional hash iteration in the key derivation. As you see here, OSCORE master secret and OSCORE master salt is now, there's now a shorter label. And that means that that is sort of new. That means that that's the breaking change, basically, when everything up to this point is the same, but when you derive the OSCORE master secret and salt, you would now get new values. And the test vectors are updated on this point. Another update related to connection identifiers, where there was a request that to mention that you actually don't need to have support both integer and byte string connection identifiers. An endpoint may choose to select a specific range and specify that in the application profile. And there's updates to security considerations, IANA considerations, and clarifications. So that's the other updates. And with that, we have addressed all open issues, and now we're just waiting for the new issues coming from the hackathon and from these excellent inputs from the analysis we've heard today. For the traces document, the situation is similar. We have a new version in the GitHub, and we have no open issues related to that. Just a reminder, the traces document, the purpose of that is to help implementers to get detailed printouts with intermediate steps. So you could go basically line by line through your code and verify. That's been confirmed to be very useful, but it's not a complete set of test vectors. It's just two specific traces, two specific test vectors, which are annotated carefully. And the change we've made since version 0.0 is that we have, as is seen here, we used to have two traces, we still have two traces, The one with static Diffie-Hellman used to be curve 25519. In the new trace, it's actually P256. The signature one is still EDDSA, but we have now included real X509 certificates, not the dummy ones that was mentioned previously in this session. There is also two more additions. There is an example of cybersuite negotiation on the static Diffie-Hellman trace, and there is an explicit mentioning of Y coordinates, which also been requested. And we reversed the order of the two traces, just an editorial here. But basically, we have all the changes that was requested on the traces. And that leaves us with the test vectors, and I think I can skip now to the last slide. I only have a minute left. So the next steps, we propose to now take what is done in the master branches, the master branch, and submit a new version, because that has been, we have basically completed all the reviews and all the old issues. And we get comments from people who read the old versions and think that ad hoc 12 is the latest version, which it is, but there are some changes now. So we think this would be the right moment to actually start progressing the drafts again. And after that, we'd like to obviously address the review comments we've got. And when we are done with that, we hope this is ready for working group last call. So those were the documents, and then the next step is also the current issues are about test vectors. So that's what we want to progress next. We should set up a breakout meeting this week, and Marek has already done very good input here, and he's proposed to help out with making the test vectors more available. So I'm done. Thank you. Any comments or questions if we have the time? Otherwise, on the mailing list.
Yeah.
Sure. Okay, so any quick comments on the changes or clarifying questions? If not, I guess the kind of next steps is on here, and that's the one we were kind of wondering about. So we had agreed that we'd try and keep draft 12 stable while the analysis was happening. So maybe the right thing to do is, now that we know that some people are working on doing analyses, to poll them and see would it delay or upset them if we move on to 13, or would they find it okay? We kind of know who the set of people doing work is now, right?
Yeah, exactly. So we know this is 4 teams that are involved right now, and I think it kind of makes sense to reach out directly and work directly with those folks. And once again, I invite everyone who might we not be aware of that is working on the security analysis of ad hoc to let us know, such that we could coordinate about this. So do we have any objections to this plan or that Joran is proposing?
Well, if we reach out to those teams and then let the list know, and then we can.
Okay, I was thinking. Okay.
I wouldn't worry. So John in the Jabber chat raises the draft expiry, I guess. I don't think we should be concerned with that. Drafts don't really expire anymore. So I think the stable reference versus the work ongoing is the question.
So Stephen, just to clarify, so essentially you are proposing first to coordinate with the teams, and then to make a decision on the mailing list and to let the mailing list.
Yeah, I expect nobody on the mailing list will object, but we should just. We decided on the mailing list that we would do this. If we're going to just slightly change the plan, we should just do that, confirm that on the mailing list.
So yes, the decision to freeze the specification was until further notice, so it is up to us right now. John, do you want to say something?
Yeah, I think we in the room here knows what the expired draft is not the end of the world, but people outside the IETF sometimes believe that means the work has been dropped. So I think I think the expiry means something, and we should not let it expire. I think if the implementers absolutely don't want a new version, I think we should just take the 12 version and resubmit it as at 13 without any changes, just to avoid expiry. Otherwise, I 100% sure we will get people asking about if the work has been dropped because it's expired.
So if I understand correctly, the draft will expire on 23rd of April. So that gives us 1 month to decide and to proceed with the next steps. Essentially, seeing if the teams checking out with the different cryptanalysis teams whether they can update their models and their work to the latest specification. So I think that makes sense. In the worst case, John, I tend to agree with you that yes, we should keep the draft alive, and as it sends the wrong signal to the people outside of the working group. So, but let's worry about it in the days before the actual expiry, not now. So with that, we are done with all the agenda items. Do we have any other business? Yes.
Yes. I just wanted to say I didn't talk about the test vectors here. So people who are interested in test vectors, pay attention to what's happening will happen in the GitHub now. So as we start to make that seems to be the last part, which we need to take some action on. And there's been a lot of interest in particular the JSON test vectors, because that's the bulk of the tests that you may want to do on your implementation. So the only thing that's needed, I think, is to get more structure on that. So we'll schedule a breakout during this week, and if you're interested, just let us know. Otherwise, we invite the people that we think are interested in that.
Okay, thank you, Göran. So, yeah, do we have any other business? So I hear none. So I propose we conclude the meeting and keep the work going on GitHub and on the mailing list. Thank you all for attending.
Thanks all. Thanks to the note takers. Right, great. Okay, I gotta go and disappear and do a lecture.
Oh, okay. I'll take the notes and turn them into minutes.
Fantastic.
I mean, yeah, but they seem they seem like a book. Seems good. All right.
Yeah, so I guess the thing to do is we could just send a mail to the various teams.
Okay. Yeah, it makes sense, really. I mean, Göran is...
They may well come back and say, oh, what changes are you planning?
They will.
We can just point them at the GitHub repo.